Hello there. In this video we're going to introduce a very powerful and useful technique in statistics, and that is known as moment generating functions. And this is heavily tied to probability theory as well. So in this video we'll describe what a moment generating function is, a couple properties associated to it, do a couple examples as well, and in the video we'll do a couple more examples associated to moment generating functions in a couple examples of probability mass functions. So let us recall just a couple things from our standard statistics and standard calculus courses. So recall that if x is a random variable, but let's just assume without loss of generality for the time being that this x is a discrete random variable. So if x is a discrete random variable, there's two properties that it satisfies. First, the expectation of that random variable, x, and let's also introduce another random variable, y. So let's assume if r random variables, then e of x plus y is going to be equal to the expectation of x plus the expectation of y. And remember what the expectation of a random variable is. So remember the expectation of random variable x is defined to be equal to the sum across all little x values of x times the probability mass function associated to that particular domain value. Also, 2, the expectation of a constant times that random variable is going to be equal to that constant times the expectation of that random variable. And this is true where a is some constant or scalar. Also, recall the Taylor series. So the Taylor series of the function y is equal to e to the x. So the Taylor series for e to the x is equal to the infinite sum from k is equal to 0 to infinity of x to the k divided by k factorial. So we're going to combine both these to create what is called the moment generating function. So we're going to define m sub x of t to be equal to the expectation of the random variable e to the power t of x. And here t is some real number and x is a random variable. Alright, so what exactly is so special about this? And this is what we're going to call the moment generating function of x. And we'll explain how this ties into like the first moment and the second moment of the random variable a little bit later. So let's look in particular at this expression on the right hand side in the Taylor series perspective. So the Taylor series perspective of e to the tx is going to be equal to, so e to the tx we know is going to be the sum from k is equal to 0 to infinity of tx raised to the power k divided by k factorial. So we can expand this term by term to sort of understand exactly what we're looking at here. So we have m sub x of t is equal to the expectation. So when k is equal to 0, this is just equal to 1. When k is equal to 1, we just have this is going to be equal to tx. When k is equal to 2, this is just going to be equal to tx squared divided by 2 factorial. Plus, when t is equal to 3, k is equal to 3, we have tx cubed divided by 3 factorial, plus and so on. And all these x's are random variable x's and t's are just constants. So I can distribute this expectation over this infinite series. So we have this is equal to the expectation of 1 plus the expectation of tx plus the expectation of t squared over 2 factorial x squared plus the expectation of t cubed over 3 factorial x cubed and so on. So notice that we have constants inside of these expectations because remember t is just a constant and the expectation of 1 is just equal to 1, so nothing special about that. So we can write the moment generating function of x of t is precisely equal to 1 plus t times the expectation of x plus t squared over 2 factorial times the expectation of x squared plus t cubed over 3 factorial times the expectation of x cubed, and so on. So what exactly do we have here? So notice that expected value of x, this is the first moment. And some people refer to the first moment as the mean of the random variable x. But nonetheless, the first moment measures central tendency. If we look here, this is what we usually refer to as the second moment. So the second moment usually measures variation. And over here we have what we may refer to as the third moment. And the fourth moment would follow after, and they have some interpretations that we'll get to later, but we'll just, discuss them at a later time. But at least notice that we have the first, second, third, and so on moment in this expression. And some people even refer to this first term. This is the 0th moment, which represents the total probability, because the sum of all the probabilities of the probability mass function should be equal to 1. Okay, cool. So we have this expression. So the moment generating function at least relates the moments to one another. So let's see if we can get a couple properties here. So if I evaluate the moment generating function at t is equal to 0, notice that everything that has a t next to it is going to disappear. So we're just going to be left with 1. So this is the very first property that is easy to verify. The second property, so we're going to take the derivative of m with respect to t. So we're going to take the derivative with respect to t of 1 plus tex plus t squared over 2 factorial ex squared plus and so on. So remember, we're differentiating with respect to t, so everything with x in it is a constant as far as the t is concerned. So the derivative of tex is just going to be equal to e to the t, or ex. The derivative of t squared over 2 factorial is just going to be t, and we have the ex squared there. And then if we look down the line, we'll have t squared over 2 factorial times ex cubed, and that pattern is going to continue onwards. So if that is the case, so this is the derivative of our moment generating function m. So from here, what can we get? So the derivative of the moment generating function of x evaluated at 0, so everything with t in it is going to disappear, so we're just going to be left with the e to the x. So notice that when we evaluate the original, we get the 0th moment. When we evaluate the first derivative of the moment generating function and plug 0 in, we get the first moment. So will this property continue? Well, we can try. So let's look at the second derivative of our moment generating function. So that is going to go to 0. That's just going to go to ex squared. Derivative of t squared over 2 factorial is just going to be t ex cubed, and then we're going to have a t squared over 2 factorial ex to the 4th, and so on, right? So if that is the case, then what do we get? Well, we get the second derivative of our moment generating function of x evaluated at 0 is equal to the expectation of x squared. And what is this? Well, this is the second moment. So we should be able to see a pattern here. And we should be able to see a relationship between the moments and the derivatives of the moment generating function. So with all of these properties considered, then we have a very, very important observation to make. So the expectation of x to the m, or the nth moment of x, is just equal to the nth derivative with respect to t of the moment generating function of x evaluated at t is equal to 0. And this is a very important result. All right. so let's see if we can do a quick example of how to use these types of things. So let us assume that the moment generating function, so example, the moment generating function for some particular random variable x of t is equal to e to the t. In the next video, we'll describe how to actually generate this function. So, as we can see, the 0th moment is going to be equal to e to the 3 times 0, which is going to be equal to 1. Right? So that's a good thing. So the sum of all the probabilities must be equal to 1. So what about the derivative? So the derivative of the moment generating function is going to be equal to the derivative with respect to t of e to the 3t, which we know to be equal to 3e to the 3t by the chain rule. So if that is the case, then the first derivative of the moment generating function evaluated at 0, which is equivalent to the first moment of x, is just going to be equal to 3e to the 3 times 0, which is just equal to 3. So that is the 0th moment, that is the first moment, or the mean, right? So we can continue onwards with this process. So the second derivative of our moment generating function evaluated at t is just going to be equal to the derivative with respect to t of the first derivative, which is simply the derivative of 3e to the 3t, which we know to be equal to 9e to the 3t. So if that is the case, then that means the second derivative of our moment generating function of x evaluated at 0 is going to be equal to, equivalently, the second moment of x, which is 9 times e to the 3 times 0, which is equal to 9. So that is the second moment of x, and this is the first moment of x. So from these two things, what can we actually generate? Well, recall that the variance of a random variable is equal to the second moment of the random variable minus the square of its first moment. So if that is the case, that means the variance of this random variable is going to be equal to 9 minus the first moment squared, which is equal to 0. So if that is the case, then that means the standard deviation of x is going to be the square root of 0, which is equal to 0. And sometimes we denote, again, the variance to be equal to sigma squared of x, and we sometimes refer to the standard deviation and notate it as such as sigma of x. So remember that useful property as well. So this is just some basics according to the moment generating functions, and just a basic example, assuming that we know what the moment generating function is equal to. And we'll do some examples in the upcoming video.